building or in the apartment right above me, so I really apologize for any noise because they've been so loud this morning.
That's okay. Nothing you can control.
Okay, so for today, I don't know if you came to other review sessions, but I kind of just like to let it be led by whoever is here. So I have all of the questions from the final review, and I also have a few other just review problems that you may or may not have seen before. So if there's anything from the final that you want to go over, I can go to those questions first, and if not, then we can go through the practice problems.
I don't mind just going through the practice problems.
Okay, awesome. So we can do that. And then let me just, Lance, is there anything that you wanted to go over from the practice final? You can say in the chat.
Hey, yeah, sorry, can you hear me?
Yes, I can.
Okay, cool. Sorry, I was just getting a second to get set up. Yeah, no, I'm good to just kind of go over it and run through it.
Okay, awesome. And then if we have any other people show up, then, we can see what they want to do. But yeah, let's start with the practice problems. So let me get down to that page. There we go. Okay. Okay, so this one is about isomorphisms. We are given two versions of the cube graph, and we want to show somehow that they are isomorphic. So there are a few different ways to show that something is isomorphic, but what I find really helpful, at least when I'm trying to figure out an isomorphism, is drawing it the way that I would expect to see it. So this cube can be drawn as this square, but we just need to kind of rearrange it so that it looks right. Mm-hmm. So we'll draw each of these dots in. Not the prettiest copy by any means, but it'll do the trick. Okay, so now we just need to figure out which vertices correspond. So let's start by saying that we can put 1 right here. So if 1 is right here, then what is this vertex going to be?
Sorry, I didn't see which one you were pointing at.
Oh, wait. Is it not? I know, my screen sharing's been having difficulties. Let's see. Is that showing up?
Yeah, now I can see it.
Okay.
So that one would be 5, right?
Yeah. And then we can do the same in this other corner. We can put 2 here, and then what does that make this vertex?
6.
Yeah. So let's fill in the rest of these.
And we could have hypothetically done it the other way too, right?
Yeah.
So like have 5 and 1. Okay, cool.
Yeah. And the important thing here is that you just need to have a mapping to each vertex. So we can rewrite this as a mapping, and we can say that 1 is going to 8 and 2 matches up with 10. And we can go through that for all of the vertices. So you could do it, you could do that same step even if you drew it the other way. So we'll write out 3 goes to 9, 4 maps to 15, 5 maps to 12, 6 maps to 14, and 7 maps to 13. Okay, so that's one way to write out an isomorphism.
And I know it's a decent enough proof, right? Like, so we could just do this on the exam, and that would be.
Yeah. Yeah, since it says show instead of proof, and since we haven't gone over isomorphisms, I doubt we would throw any proofs at you for that. But yeah, so are there any just general questions about isomorphisms? Because I've seen a few of them in Piazza.
They're pretty straightforward to me. It's just trying to draw it so it's that they look the same without like mapping them, I guess, so they look the same without changing any of the features of the graph.
Yeah, the visualization can be pretty tricky sometimes. So yeah, just takes a little bit of practice.
I think for me, for on isomorphism, so I think proving them or like showing these two are isomorphic is fine. It's when I'm asked to show they're not isomorphic because I kind of go through that checklist of like, oh, it needs to be, all right, they have to have the same vertexes of the same degree and stuff like that. And sometimes I do all of that and they match up, but they're still not isomorphic to each other because like maybe that can't be mapped or something. So sometimes that's a little hard for me to visualize.
I think you're asking about the homework, or at least, was this when you were working on the homework question about isomorphism?
Yeah,
that one was really hard. So there were a couple. There was the one about showing that they're not an isomorphism and about finding the two that were. So with finding something that's not an isomorphism, there are a few different ways you can do it. I think, at least for me, the easiest way is to find an edge that should be there, but it's not. So with the problem on the homework, I said, or at least the explanation that I guessed when I was working through it was that edge that is on the first graph should be on the second one, and it's not. And specifying, like, say that we had some other edge here that went to E, and this vertex does not have any kind of similar edge from 5. So saying like there should be a vertex that goes from, or let's see, that would be 8. Sorry, not 5. There should be a vertex that goes from 1 to something that is not 5, 0, or 3, but there's not.
Gotcha.
Another way is to do with degrees. So to say, like, there were a few different people who, for the homework question, put every vertex with degree 3 is connected to 2 vertices with degree 2, I think. And then in the other one, that wasn't the case. So yeah, there's a number of different ways to go through it, but just finding one of those is sufficient.
Okay, cool. That makes a lot more sense because I was like looking at it and I'm like, I know it like doesn't add up, but how do I write that in words? So that makes sense now.
Okay, awesome. So let's go on to our next practice problem. And this is going to be a proof, which we all love. Graph proofs are so much fun. Okay, so a finite graph means that it has a finite number of vertices and edges, and all the graphs that we deal with have been finite up to this point. So we want to prove that every simple and finite graph has 2 vertices of the same degree. Okay, so at least in my opinion, the hardest thing of figuring out a graph proof is just knowing like what you're even supposed to do, because it's kind of hard to just get started. So do either of you have any ideas? Like, there are no bad ideas, just like guesses for what might be like methods, previous proof methods that we've used that might be able to solve this.
All right, full disclosure, I'm terrible at graph proofs, but I think maybe you could just like develop a test graph. So give like the vertices of a simple connected graph and then be like, oh, look at this. I mean, I guess that wouldn't work because it has to be proofing for everyone, which kind of indicates to me it might have to be an induction proof, but I don't know.
Okay, I like that you went to a proof method, because that's usually what I try and guess first, is like just go through the normal proof methods and see if any of them could apply.
My brain just goes to contradiction because like I think it would be easier to find a graph, like try to see if there is a graph that doesn't have 2 of the same degree vertices, and then if you can't prove that, then you're proving that contradiction or whatever.
Yeah, I think proof by contradiction is really popular with graphs, so that is a good instinct. And honestly, it's totally possible that both of those methods would work just fine. I haven't gone through those proofs, so I couldn't say for sure, but the solution that we've got uses the PHP. So let's do that.
Okay.
So we'll use the pigeonhole principle. Okay, so the way that we can do this is, let's think how the pigeonhole principle usually applies. We want to prove that somehow there are 2 things in the same bucket. So in this case, the same bucket would be the same degree. So our number of buckets is going to be all the different possible degrees. And that kind of gives us a hint that we want to think more about which kind of degrees there are. So let's assume that there is a graph G that is a simple finite graph. Okay, and then each of the vertices, let's see, each vertex has, or let's say is connected to blank other vertices. So that kind of tells us the degree. So what are the options for the degree? Let's say simple finite graph with n vertices. Okay, so what is our range for the degree of any given vertex in G? If we start from a low end and go to a high end, what are we looking at?
I would just assume it'd be from 0 to n because you're either not connected to any or you can be connected to all.
Yeah, super close. So we're going to put n minus 1 though, since...
Oh, because you can't be connected to yourself. Simple.
Since it's simple, yeah. So we'll say that, let's fill in this blank. To 0 to n minus 1 other vertices. Okay, so now let's say we can, this is kind of where it gets to a weird jump where it seems like, why would you do this? But we wanna somehow prove, without going through like every single possible case, that we have two vertices of the same degree. And the easiest way to tackle that is to just use these endpoints that we've created. So we can say, so let's break it up into cases. And our first case is going to be that there exists a vertex with degree n minus 1. And yeah, so this means that this one vertex, let's call it U, is connected to every other vertex in the graph. So that means what about all of the other vertices in the graph?
They all at least have to have a degree of 1 because it's connected to them.
Yeah, exactly. So all vertices in G have degree 1 to n minus 1, somewhere in there. Okay, so how many possibilities is that? If every vertex in G has degree 1 to n minus 1, how many options are in this range in terms of n?
There'd just be n, right?
Yeah. So they all have n options. To connect to. All right, let's see. Sorry, I misspoke. N minus 1 options.
Okay, yeah.
Okay, so, but there are n vertices. And this is where a pigeonhole principle can come in, because if there are n vertices, but there are only n minus 1 options, then at least 2 of the vertices have to have the same degree. So by PHP, at least 1 other vertex. Or yeah, sorry, not 2. At least 2 vertices have the same degree. Okay, let's take the other case, which would be where one of the vertices has degree 0. So we're going to say there exists a vertex U with degree 0. Okay, so that means that somewhere in this graph there is some lone vertex, and then there's all the other ones. And these may be connected to each other in some way, but this one will not be. This one isn't touching anything else.
Mm-hmm.
So that means that, let's see. So this means that all other vertices have degree, we could still have them have degree 0, but this time we can't have them go to n-1 different options because that would include this vertex, which can't have anything connected to it. So our new range is n-2. And because it's from 0 to n-2 in this case, there are still n-1 options and only n vertices. So by the PHP, again, at least 2 vertices. 2 vertices have same degree.
Sorry, you might have just said this. Why is it n-2?
n-2. So usually, like in any other graph, we can go from 0 to n-1, but because U, this little vertex right here, U doesn't connect to anything else. So now we have n-1 other vertices.
Gotcha.
Okay, awesome.
That makes sense, yeah.
Okay, does all of that make sense?
Yeah, it does.
I know it's a lot harder when you do it yourself, but yeah, unfortunately it just helps to do lots of practice. So as long as you understand the proofs, it'll help to figure them out again in the future. Okay, moving on, we have a contrapositive proof. Since this one is pretty similar to a lot of different proofs that we did, I'm gonna have you work on this one by yourselves for just a couple of minutes, since you'll be more familiar with it, and then we can talk about it. Okay. Okay, so let's go through this one. Our hint is that we want to use the contrapositive, so let's start with that. What is going to be the contrapositive of the problem statement?
So yeah, I'm pretty sure I know, but I was just about the or. I'm not 100% sure exactly how that would work. But so basically it would be not Q, then P, right? Is like the
Not Q, then not P.
then not P. Okay, that's okay. So what I had written was if X is odd, or Y is odd, then X squared times the equation or whatever is odd as well.
Oh, there we go. Sorry, I was muted. So there are only a couple little things that need to be fixed here. So the first thing, so let's break this up. So let's call this section P. Oh my goodness, that is so loud. I'm so sorry.
You're good.
That construction's driving me crazy. Okay, X is even. Let's call this Q. And then we have an OR, and then we have Y is odd. So let's call that R. So P implies Q or R. So if we take the contrapositive, we're going to end up with not Q or R implies not P. So the only difference here is that this, so this will be not Q and not R because of De Morgan's law, which means that our contrapositive is going to be X is odd and Y is even. So let's make those little changes. Y is even. Okay. And then we'll kind of move this up to the top. All right, so now, and this is, and this won't always be the case in contrapositive. Sometimes you do it and you still have to split by cases, but it is super helpful for our purposes that now we don't have to split into cases because our hypothesis just assumes that X equals 2A plus 1 and Y equals 2B, where A and B are in the set of real numbers, or in the set of integers. Okay, so what's our next step?
That's kind of where I get stuck, so.
So do we need to substitute these values in for
Yes.
the, all right.
So now that we know the values of X and Y, we can make a substitution and say that our expression is equal to 2A plus 1 squared times 2B plus 3. Okay. Let's multiply this out, which will give us 4A squared plus 4A plus 1 times 2B plus 3. Okay, this is where it starts to get a little bit tricky because we're not going to do, we can multiply all of these terms out and we can determine that it's odd that way. But we're going to take a slightly different approach because doing this multiplication is gross and we don't want to. So let's instead use what we know about the product of integers and we can use that. So we can see that 2b plus 3 is going to be an odd number. And we can rewrite it as, let's see, it would be 2b plus 1 plus 1. Which we can say is 2, let's call it 2m plus 1. And 4a squared plus 4a plus 1 can be rewritten as 2 times 2a squared plus 2a plus 1. So that can turn into 2n plus 1. So now we have that x squared times y plus 3 is going to be equal to an odd number times an odd number. And the product of two odd integers is also going to be odd. We can just say that that is known, but if you wanted to, if this were on a test and we didn't specify, it would probably be a good idea to also go through that proof, that the product of two odd integers is still odd, which is a pretty simple proof. But yeah, so then we know that x squared times y plus 3 is odd, and since the contrapositive is true, then the proposition is true. Is true. Okay, any questions on that one?
So hypothetically, if we didn't see we could just factor out to create like an odd or even number, we could have like painstakingly multiplied those through and it still would have worked out, right?
Yes, yeah, we can, if you want, we can go through that right now, like we have the time.
It's okay.
But yeah, it would work out that way as well.
Gotcha.
Okay. If there's nothing else, we'll keep on going. Okay, so this one is an exercise on induction. These are super important. I can almost guarantee that these will be on the final. That's just like 2100 classic torture. So it's super important to know how to do these ones. And yeah, we've gone over, at least I know that other TAs and the professors have both gone over different ways to do induction, because I think everyone kind of learns it slightly differently. So yeah, so this might not be the way that you've seen it in lectures or anything, but personally I find this to be the easiest way to go through induction, which is to just set these up as why can I not think of the word? Series, I believe. But yeah, so we can set that this is going to be equal, instead of using the summation, I think it's easier to say that an is equal to an minus 1 plus n cubed. And those are equivalent statements. And then we just need to set the base case, which is a1, and that's going to be equal to 1 cubed, so a1 equals 1. And then we can set bn to this other formula, and we get bn equals n squared plus n times n plus 1 squared over 4. Okay, and the reason that I find this easier is because now our problem statement is p of n. We just want to show that a of n equals b of n. So it's just kind of more of a notation difference that makes it a little bit more simple. Okay, what is our base case going to be?
P of 1?
Yeah. So we already know that a of 1 is equal to 1. So now let's do the same thing for b of 1. And we get 1 squared times 1 plus 1 squared over 4. And that gives us 4 over 4, which is 1. So a1 equals b1, and the base case is true. All right, so now let's move on to our inductive hypothesis. And here we have the option to use n minus 1 or n. So do either of you have a preference for which one we go through? Or we could even do both too, if that would be helpful.
I'm fine with either one. I don't care.
So personally, I prefer usually to do p of n minus 1, just because it ends up working out really well with this notation. Mm-hmm. So if we assume p of n minus 1, then we assume that a n minus 1 equals b of n minus 1. And then we also, in this step, it's good to find what b of n minus 1 is, because we'll probably need it later. So we just need to plug in n minus 1 for each of these over 4. Okay. So let's see. That is also equal to n minus 1 squared times n squared over 4. So now let's move on to our inductive step. And we want to prove now that a of n equals b of n using our inductive hypothesis. So this is where it becomes helpful to use the p of n minus 1, because we can say, let's just go ahead and substitute. We know that a of n is a n minus 1 plus n cubed, and b sub n is n squared times n plus 1 squared over 4. Okay, so what can we do here? What substitution can we make?
So we can use our inductive hypothesis to plug in for a sub n minus 1, right?
Yeah, so this is equal to b sub n minus 1. So we can substitute our n minus 1 squared times n squared over 4 plus n cubed is going to equal n squared times n plus 1 squared over 4. Okay, and now it's just a matter of algebraic manipulation to figure out how these two are equal. So let's start by getting everything onto the same terms. So let's multiply the n cubed by 4 over 4, and that will end up giving us n minus 1 squared times n squared plus 4n cubed over 4 equals n squared times n plus 1 squared over 4. And because everything is over 4 now, we can kind of ignore it. So we can just solve for this part and try and figure out how these two are equal. We don't have to worry about the denominator at all. Okay, so any ideas where we might want this to go? Any ideas how we can manipulate the left-hand side to get the right-hand side?
Is it useful to expand the binomial? I don't know.
Yeah, so let's see. Let me think on this for a second, because it is a little bit tricky. Yeah, I think that it's possibly worth it in this case to go ahead and expand these terms. There are, like, when you do the n to n plus 1, you can do some tricky factoring and stuff, but I think in this case it's easier to just go straight forward. So we're gonna have n squared minus 2n plus 1 times n squared plus 4n cubed equals n squared times n plus 1 squared. Okay, so we have our, let's see. Let's actually, yeah, let's multiply it in and see where we get. Honestly, I'm not 100% positive that we're going in the right direction, but sometimes that's kind of what you have to do to get to the right place. Okay, yeah. Okay, so in order to get our n plus 1 squared, we want to somehow find a term that is n squared plus 2n plus 1, because we know that that is our, we know that that's equivalent to n plus 1 squared. Okay, so if we combine like terms here, we get n to the 4th plus 2n cubed plus n squared. And now we can factor out n squared here. And we get n squared plus 2n plus 1, which is exactly what we were looking for. And now we can rewrite this as n plus 1 squared, and they are equivalent. Okay, it's hard to get lost in the weeds on induction proofs, but does all of that make sense?
Yeah, it did. There's another induction proof that's in like the practice final exam. Can we go over that? Because I'm not good at induction proofs, and I know I should be.
Okay, yeah.
I was just going to ask, so I think like that made a huge amount of sense. The thing that's hardest for me is actually transforming, as stupid as this sounds, transforming the summation. Can you just like briefly go over how you did that, like just to the a sub n and stuff like that?
So generally, let's just look. Here, I'm going to copy this down so it'll be easier for me to remember. Okay. Make it a little bit bigger. Okay, so usually when we have a summation, the way that we would solve it is we're starting at I equals 1, we're going up to n, and for each of these, we're going to add it. So we're going to say we're going to have 1 cubed plus 2 cubed, oops, plus 3 cubed, and so on, so on. Okay, so in each of these cases, oh my goodness. Okay, so let's say that n equals 3. So we're only going up to 3. We don't have any more of this. And basically what this is doing is by the time you get to this third term, you have your previous 2 terms and then you're adding on this new one. And you're going to do that in every case. So if we change this up to 4, then now we would be taking everything that we added in when n was 3, and then we're adding in a 4 cubed. So in any case, we're taking all the previous terms and adding them to our new one, which means we could write this, if we say that this is a n minus 1, then we just need to take everything that came before it and just add on our new term, which we're just going to sub in the n for the I because it keeps it consistent with variables. And now in each of these cases, so let's go back to, let's just say n equals 1. So in our case of the series, that would just be 1 cubed. And in the case of a n, we just have a 1 equals 1 cubed, which is also 1. Okay, now let's say that the series goes up to 3 like before. So in the case of just writing it as a summation, we would want to add 2 cubed. And so this is, actually, sorry, I'm going to go back. We're going to say n equals 2. I think that'll be an easier step. Okay, so the summation is 1 cubed plus 2 cubed, and our a2 is going to be a sub n minus 1, which is 1 plus 2 cubed. Okay, and then here's where it's more helpful. So now we say that n equals 3, and we still want to use all the terms. And basically, these 2 terms represents a sub n minus 1. Does that make sense? Like this is the same as a2. So now when we do a3, we have a sub n minus 1, which is a sub 2, plus our 3 cubed. And that's the same thing that we have up here. So,
Gotcha.
Closing arguments is that in any of these cases, especially with summations, in order to write it as a n minus 1, we just need to add on whatever is right here. So if we had like a more complex term that was like I plus 3 squared times 2, then we would just add that on to our a sub n minus 1. Does that help at all?
Yeah, no, that's awesome. Thank you.
Okay, great. So yeah, let's go up to that exam problem. Just give me 1 second to find it.
It's problem 8, if that helps you at all.
That does help me a lot. Thank you. Okay. Problem 8. And then let's pull it up here too. 8. All right. Okay, so yeah, let's use the same thing that we were talking about last time, what we just went over, to say how we would write this as a sub n.
So in this case, you just do a sub n equals a sub n minus 1 plus I times I factorial.
Yeah, and then I'm just going to switch them out for n's. But yeah, that's exactly what we need. And then let's let b of n equal this other formula up here, which is n plus 1 factorial minus 1. Okay. So our problem statement, again, is going to be just that a of n equals b of n. And our base case is, again, going to be p of 1. So for a of 1, and I guess I should have gone over this when I was explaining how to rewrite these summations as well, which is that when you're finding the base case, you just want to plug the 1 directly into the variables. Okay, so in this case, we'll just have 1 times 1 factorial, and that ends up being 1. And then for b sub 1, we have 1 plus 1 factorial minus 1, which ends up being 2 minus 1, and we get 1 for that as well. So the base case is true. Okay, now for the tricky parts. Let's start with the induction hypothesis. And give me 1 second to look at this. I want to go through with the p of n this time, but I just want to make sure I understand the steps, because when I solved it, I did p of n minus 1. Okay, so yeah, let's assume p of n, which is that a of n equals b of n. So we're just going to assume that that's the case. And in our inductive step, we want to prove p of n plus 1, which is that a of n plus 1 equals b of n plus 1. Okay, so it ends up working out similarly. If we write out, oh my goodness, that construction is so loud. Okay, a of n plus 1, let's just write out each of these terms so that we know what we're looking for. So a of n plus 1 is going to be we're just substituting n plus 1 in everywhere that there's an n. So we get n plus 1 times n plus 1 factorial. And that ends up being just an plus n plus 1 times n plus 1 factorial. Okay, and then for b of n plus 1, we have n plus 1 factorial minus 1, which is equal to n plus 2 factorial minus 1. Okay, we just want to show somehow that these are equivalent. So we have a of n plus 1 times n plus 1 factorial equals n plus 2 factorial minus 1. So we can do, similar to last time, we can do a substitution. So let's sub in our b of n. All right, and that means that now our proof becomes b of n is n plus 1 factorial minus 1 plus n plus 1 factorial equals n plus 2 factorial minus 1. Okay, so now let's rewrite these. Give me just 1 second to figure out what this is saying. Like I said, I haven't worked through this one yet.
Okay.
Let's see. That construction is definitely not helping.
Yep.
Okay. So maybe not. Okay. Let me me see if this will, again, no promises that this is working it out quite right, but oh wait, let's see. Sorry. Okay, yes, okay. So we eventually want it to be in the form. Okay, I'm gonna have you both help me and see if we can figure this out. This is what we want it to eventually become. This left-hand side, or not with K's. Let's use n's. N plus 1, n plus 2 minus 1. Okay. Let's see. Factorials are always tricky to like manipulate. So we already have our minus 1. So I'm going to move that up to the end so we can keep track of it. Okay, so my best guess is I'm assuming there's like an n plus 1 being factored out, which would give 1 plus, and yes, okay, got it. Sorry for that. Okay, yes, so let's factor out, we're gonna factor out an n plus 1 factorial, and that leaves us with 1 plus n plus 1, and then minus 1. And then this can be rewritten as n plus 1 factorial times n plus 2 minus 1, which is this term that we've got down here. Okay, and now we can rewrite this. So if we have n plus 2 times n plus 1 factorial, that can be rewritten as just n plus 2 factorial. And we have what we were looking for. Did the factorial manipulation, specifically like this step right here, does that make sense to you? Because that step is used a few times in factorials, and it's kind of not obvious.
You were saying that changing the, sorry, I couldn't see where your cursor was or whatever, it didn't show up.
These last two steps right here.
Yeah, that makes sense to me.
Okay, awesome. Okay.
So wait, are you like using the factorial or something? I'm very confused.
So yeah, that totally makes sense. So usually if we have n factorial, that is going to be n times n minus 1 times n minus 2 all the way up until you get 0. Or not 0, until you get 1. Okay, so if you have n plus 1 factorial, then you're going to start with n plus 1 times n minus 1, and so on. So if you have any type of, like if you had n factorial and then you multiplied it by n plus 1, then we can see, like here, I'll move this down a little bit. So n plus 1 factorial, the only difference is that you multiplied by 1 higher. So if you have n plus 2 factorial, then that's equivalent to saying n plus 2 times n plus 1 factorial. Does that make more sense?
Yeah. Okay, gotcha.
Okay, awesome. So are there any other questions on that? I know I kind of got lost in there for a second.
No, you getting lost helped me think about it more, so I'm good.
Okay, awesome. All right, so I'll kind of zoom out so you can take that all in for a second. Do we just want to go back to the regular practice problems now that we went through a couple of induction from the practice quiz?
Yeah, I'm good to go back to whatever now.
Yeah, that's good with me.
Okay, this is another one that we see a lot of struggle with, is doing an element-wise proof, but with very specific sets. So let's look at this problem. We want to show that A is a subset of the intersection of B and C. And we have to, in order to do that, we have to show that any element that's in A is also in B and C. So that's the basic outline of what we're trying to do here. Okay, so let's go ahead and split it up into two cases. So first we want to show that being in A implies that X is in B. And then for our second case, we'll go through X is in A implies that X is in C. So if we let that some element X is in A, then what can we say that X is equal to?
Sorry, I'm just trying to write this down as fast as I can.
No worries. Okay, so we want to use the set that was given to us. So any element that is in A can be written in the form 6k plus 1, where k is in the set of integers. And remember, we eventually want to show that X is equal to 2n plus 1, where n is in the set of integers, because that's the definition of B. So what can we do to get what we want here?
Okay, sorry. I also just finished writing down the problem. So did you just arbitrarily decide that X is an element of A? Because that's how we're going to prove it?
Yeah, so...
Because that's not given, right?
Yeah, technically it's not given, but it's just because, you know, if we were doing just like a normal element-wise proof, that's always going to be our first step, because in order to show a subset, we need to show that this implication is true. And if the hypothesis is false, it doesn't really give us any important information.
Gotcha. Okay.
So yeah, we always want to assume that X is in that first set. Okay, so this one is a little bit more straightforward than some of them are, but we can factor to get this form. So if we pull a 2 out, we end up with 3k plus 1. And then this can just simplify to, actually, we don't even need to write another step. That already simplifies to 2n plus 1 by closure under multiplication. Okay, and then for our second case, it'll be super similar, except this time we want to show that X is in C. So again, we'll let X equals 6k plus 1. But this time our endpoint is 3m plus 1, where m is in the set of integers. Okay, and then again, we can just factor out a 2k plus 1, and then we can say that this step happens by closure under multiplication. All right, so yeah, that one is a little bit simpler, but it'll be the same kind of way of thinking about it as you would if you had something a little bit more complex.
So the biggest problem that I have with these is figuring out what to pull out to make it look like it, because sometimes and some of the examples that they've gone through, they will add 8 and subtract 8 and pull random things out, and I'm like, how do you know to do that, I guess, is kind of my question. I get confused when they start doing that kind of stuff because I don't see that when I'm looking at the problem.
So yeah, I think the best way to kind of at least guide you towards the right place is I always start a proof by writing where I'm at and where I want to go. And that always helps me keep track of how do I get this form that I'm looking for? So in this case, our starting point is that X is equal to 6k plus 1, and our ending point is that it's equal to 2n plus 1. And that kind of helps me see what do I need to fill in this space to get where I want to go. And with some other more complicated problems, I'm trying to think of a way that I could invent one where
I know.
it's so hard to make up problems. So yeah,
if I can find one in my notes.
That would be awesome, because that's definitely not a natural step in algebra that you're used to taking, but I know exactly what you're talking about.
I have so many notes for this class. It's ridiculous. I'm not gonna lie.
Yeah, it's so these ones sometimes are really tricky because I have the same problem. Sometimes it's like if I see it, we're golden, but if I don't see it, it feels so bad. I'm just like, well, I have no idea how to manipulate this.
Okay, so I'm gonna kind of do it here. I don't know if this will be helpful since we don't really have an ending point anymore, but
Yeah.
let's see. I'm gonna hurry and write it. Okay, yeah. So let's say that you kind of like saw me work through that, so you already know the answer. But let's say that our final C is that we want to show 6K plus 5. Is that what I had? I think so. And that obviously doesn't seem possible when you just are looking at this problem, or not 6K plus 5, 6K minus 5. There we go. You're like, how can that work out? So let's see. So if I have something like this where 6K plus 1, 6K minus 5, they're like a totally different form, that's when I start thinking, is what can I change this 1 to be so that it will fill in this space? Because we already have the 6K, so we want to figure out a way to like change it. And this is where I start thinking of, okay, I know that I want to be able to factor 6 out. That's a step that I know that I want to take. So how do I use the 1 but also be able to factor out 6? And that's when I would kind of break off here and say, okay, what is some way to manipulate 6 so that we can still have 1, which would be to subtract 5. Okay, so now we can write that substitution. And that gives us K plus 1 minus 5. And then let's use a different variable here, 6 minus 5, where C is in the set of integers. Okay, does that make a little bit more sense?
Yeah, that really does, because
Awesome.
Yeah.
It's
You're like, just add 8, and I'm like, why? Why does it? But yeah, having you explain the 1, splitting the 1 up, that makes a lot more sense.
okay, awesome. All right. Any other questions with these problems? Did you end up finding an example one that you wanted to go through?
I couldn't.
Okay.
I thought I found this section, like a section with some of them, but I couldn't find one with the weird adding in it. So.
Okay. Yeah. That'll be super common. So yeah, just look for, I think that is an important tool just in any proof, is being able to say like, and that's also how I figured out eventually, you said that me trying to figure it out helped you. That same thought process that you go through is what I did for the induction proof, which is just saying, okay, I know that I have this minus 1 and I know that I want to use that. So how can I fix the rest of it to do what I want to do? Okay, let's move on. So we want to prove that this relation R is an equivalence relation. Again, this is like classic 2100. There's a good chance that this will be on the final as well. Some kind of like equivalence relation where you need to prove multiple properties about a relation or a function, very likely. Okay, so what are all the things that we need to prove in order for R to be an equivalence relation?
You have to prove that the one side is the subset of the other, then flip it, right? Or
that is for set equivalencies.
Oh, okay.
Is this like onto 1-to-1 and or no, wait, maybe is this one like transitive? God, I got all of those units so conflated. Okay, so this is what it's, oh man, transitive, like symmetric. I need to write those down on like my reference sheet for equivalence relations in like reflexive or something. I don't know.
Nice guesses. Yeah, exactly. Yeah, so that's a good thing to have on your note card. It also might be on the cheat sheet that we are attaching to the exam, but I can't remember for sure. So if you're able to look at that and double check.
I think it was posted. I'm trying to remember where it was.
I think it was like kept in the wrong place, but it is supposed to be in the right place now. I think it'll be in announcements. Let me just double check. Yes. Yeah, in the most recent announcement, final exam cheat sheets, there's a link to the final exam cheat sheet. And then let me just pull it up and double check that. Yes, so that will be given on the exam. What an equivalence relation is. Let's see. Yeah, reflexive symmetric transitive. So it also has partial order, strict partial ordering, and total ordering and strict total ordering. So the important thing with these is to know what they mean more than memorize them. But yeah, transitive, symmetric, reflexive. So let's go through, let's start with reflexive first. And in any reflexive proof, the goal is to say that for any x, whoa, my pen is freaking out. For any x that is in the set of real numbers, since that is our, that's what x is coming from, then x is related to x. So this is where we want to get to eventually, is to show that x and x are related. So in this case, let's just go ahead and plug it in. So we get 3x minus 5y equals, we want to show that that somehow equals 2a. Actually, I'm going to put this down at the bottom. So 3x minus 5y, or sorry, not 5y, 5x, is going to be negative 2x. And we can rewrite that. It seems like kind of useless, but we can rewrite it as 2 times negative x, and then that'll be 2a based on, let's see, where a is in the set of integers by closure. Okay, next let's look at symmetric. And then with a symmetric proof, we're trying to show that if x, y is in the relation, that implies that y, x is in the relation as well. So basically we're saying that 3x minus 5y equals 2a. And we want to use this that we know to eventually show that 3y minus 5x is also equal to 2, let's call it 2b. Okay, so this is actually a great example of one of those times that we want to add in something totally random, but there is motivation. Okay, so we're trying to get 3y and negative 5x. And this is kind of one of those times that you look at this and be like, I have no idea. This is a stopping point. I don't know what to do. So let's look at what we have versus what we want, which is that we have 3x and we want to be able to do something that will eventually give us negative 5x. And the easiest way that I see there is to just subtract 8x. I know that that'll be true. And then same for 5y. We have negative 5y and we want 3y. So a solution is just to add 8y. But if we're going to be adding on these terms, we have to do it on the other side too. So let's do 3x minus 5y, and then we will subtract 8x and add 8y. And then we'll do the same thing on the other side. Since we did it on both sides, that's allowed. And now this gives us our 3y minus 5x like we wanted. And this side is still even, so we can still factor out a 2 and get a minus 4x plus 4y. And this is equal to 2b, where b is in the set of integers by closure. Okay, does that make sense how we threw in the 8x and the 8y?
Yeah, that does.
Yep.
All right, so for our last little mini proof, we want to show that not reflexive. We already did that. We want to show that R is transitive. And to show transitivity, we want to show that if XY and YZ are in the relation, that implies that XZ is in the relation. Alrighty, so we are given that 3x minus 5y is some even integer, and 3y minus 5z is also an even integer. And we want to show eventually that 3x minus 5z is also an even integer. Okay. So how are we going to, I don't know, any ideas what we can do here to get what we want based on what we have?
So did you sorry, just a quick question. So for this, we have 3x minus 5y equals 2a, because that's given in the problem. Mm-hmm. And then, so is the 3y minus 5z equals 2b. Do we just do that because we're trying to prove it's transitive, so we need to like swap the variables up?
That comes from this definition right here, that y and z are in the relation.
Gotcha. Okay. Sorry.
No worries. Okay, so the first thing that I notice here is that we have the 3x and the 5z that we want. Like, we already have these terms, but we have a lot of other stuff that's kind of in the way of them. So this is kind of like not something that we've seen in proofs, but my instinct would be to add these equations, because that will be a way that we can keep both of these terms and work with whatever we have in the middle. So if we add these, we get 3x minus 2y minus 5z equals 2a plus 2b. Okay, and now we can see kind of like our silver lining already. We know we have this in the middle, but it's divisible by 2, so it won't cause any problems for us if we move it to the other side. Plus 2b plus 2y. And then we can just factor out here and get a plus b plus y. And then that gives us to our last step, where c is in the set of integers by closure again. Okay, does that proof make sense?
It did, yes. Sorry, I'm still writing.
No worries. And I can kind of like zoom out if you want to look at anything else.
Yeah, so I guess with these, what's most helpful is to write like the definition out and then write your like equation out in terms of whatever your rule is, and then just kind of solve through it. Mm-hmm. Okay, I think I'm good on this problem.
For 3x minus 5z equals 2c. Mm-hmm. Okay, so everything makes sense how we got there. That totally makes sense. I guess, how did we know we had to get to that equation?
Yeah, so that comes from this last part. In order for x and z to be in the relation, this has to be true.
Okay. Checks out.
Okay, so let's move on. Actually, psych, we're not going to move on. That is the end. Those are all the practice problems. So, yeah, at this point, again, it's kind of in your hands. You two get little advantage here since you are the only ones here. I can go through other homework or practice problems that you want, like anything from the textbook, or we can go through the practice final. Or if you feel like you're good, you're also free to leave.
I wouldn't mind going through some of the practice final ones.
Hey, awesome. So let's just start at the top here. Are there any specific ones that you want to go through? some of them are a little trickier than others.
Let me look at it really quick. I've got it pulled up.
So for the final, right, it's comprehensive and we have 2 hours to take it, right? So can we expect there to be like about double the amount of problems that there would be on like a normal test? So like somewhere around like 12 problems or something like that?
Yes, I believe it'll be around there. And I could be mistaken, but last time I was talking to Professor Wang, she said that she wanted to publish like exactly how many problems there will be once the quiz is finished. So
Gotcha.
that may be coming. But yeah, I think our plan right now is to say this may be I think our plan is to say how many questions there are and how many for each section.
Okay, cool.
But yeah, no total promises on that because I think it was still in discussion, but I think that that is the plan right now.
Gotcha. No worries.
Yeah, I'm not too picky. I kind of need a review on everything, so.
Okay, awesome.
Yeah, I'm the same way.
We can just work through them all. Well, oh my goodness, I feel like they're just getting louder just to spite me. Like they found out that I was doing something and they're like, let's just hammer even harder than we were before.
It's funny, it usually just starts right when you're talking. Like when you're silent, it's quiet, but as soon as you start talking again, it's...
Yeah, love that. Okay. And this recording is going to be so much fun. All right, so practice final. Let's start with this start question, and we can just go through each of them. I'll just let both of you go ahead and guess, and then we'll talk about it if we need to. Okay, true or false, the empty set is a member of every power set.
True, right?
True.
Yes.
Yeah.
Sure. Okay. Next one. So actually, this one, I'll be honest, the solution that's on Canvas does not make sense to me. So I'm not sure if it's a typo or if it's I'm doing something wrong. But on Canvas, this one says that it's false, and I think that it's true. I went through like each of the different cases and it looks like it's true, but yeah, we can work through this one. I'll just hurry and add a page and we'll work through it together so you can see. Maybe you'll be able to find my mistake. Okay. So we're saying that for every n that's in this set, n divides n squared. And n divides n squared means that n squared equals n times some k, where k is instead of integers. Okay, so for each of these, we need to show that this is true. So we'll need to know what n is, and we'll need to know what n squared is. So starting with n equals -1, n squared is -1 squared, which equals 1. So 1 equals -1 times k, and that's true because k can equal -1, and that would give 1 equals 1. Okay, and then for n equals 0, n squared also equals 0, and we have 0 equals 0 times k, and that could be true for any integer.
Yeah.
And n equals 1, and n squared equals 1 again. So 1 equals 1 times k, and again, k could just equal 1. So there's no counterexample, so I would say that this is true. Yeah, I'm not sure why it's wrong on Canvas.
So for
Maybe
these
it's a typo.
divisible or divides by problems, so we just need to look for, is there a possible solution where this equals the other thing? For like a divides b, it's like, okay, is it possible that this could somehow divide this number or something like that?
Yeah,
for the k value.
Exactly. There's also another way to look at it is if, let's see, if n squared over n is equal to an integer. So
okay.
In this case, like in the first case, it would be 1 over -1 equals -1. And since -1 is in the set of integers, then they're divisible.
So I guess with 0, can you still do that? Because like 0 over 0, and then you get like a divide by 0. But, or is that just fine because you can just, it's 0? I don't know.
Okay, maybe 0 is where it's off, but it still feels like it should be like, I guess maybe 0 doesn't divide 0.
Gotcha. Because I understand the logic, how it could, if that makes sense. I don't know. All right, cool.
I'm actually here. Give me just 1 second. If I can't find it quick, I will quit. But I'm curious. Does 0 divide 0? I don't think it would. Yeah, because it's undefined. Okay, awesome. Thank you.
Well,
that's exactly what I was looking for. So yeah, false because 0 does not divide 0. Okay, next one, which is just there exists some n in this set for which 2 divides n squared, which would be n squared equals 2k, or n squared over 2 is an integer. So what do we think about this one? True or false?
It's gonna be false. I guess 0 would be my only one that I would check.
So let's check with 0. 0 squared is equal to 0, and 0 over 2 equals 0, which is an integer. So this one actually does work, since 0 is just on the top.
Okay,
so
yeah.
This one will be true. All right, next one, every function from A to A is onto for every set A.
Let me look up the definition of onto really quick.
So I guess I'm just gonna intuitively assume this is true, but maybe it's not. Because so onto is right, every element in the codomain maps to an element in the domain.
Yes.
I think. Okay, and so if they're the same function, does that mean they have to? Maybe that's just the wrong intuition. I don't know. I think Zoe's frozen.
Yeah, that's what I'm thinking. I was like, guess we'll wait and see. Cool. Maybe she'll join us again.
Yeah. Rip.
Okay, sorry about that.
No worries.
Had some internet difficulty. Let me get my screen share set up. Oh, Jerica.
I'm going to make you the host again.
Awesome, thank you.
You're the host. When you left, it was like, I'm the host now. Okay.
I think what I was saying, so the function itself is what determines if each of these are being pointed to. Without knowing what the function is, we can't actually say that it's on. Because, for example, the function could literally just be 1-to-1. Like, that's the whole function, is just that mapping. And that would not be 1-to-1. Or that would not be onto.
Gotcha.
Okay. So E. For every set A, there exists a function A, with A is the domain and codomain that is 1-to-1. Okay, this will be similar to the last one. The difference is here is in the phrasing. So for problem D, it was saying every function is onto for every set. And in this case, it's saying that for every set A, there exists some function that is 1-to-1.
I mean, probably, right? I don't know.
Yeah. So every single function, or every single set, there's some function, which in most cases, or not most cases. Anyway, there's always going to be a function for which each of these only goes to, or I guess it would need to be. Anyway, you know what I'm saying.
Yeah.
I gotcha.
Okay, next one. So this one's tricky. We're looking at every set S. Actually, kind of a little bit trickier. So the number of sets in S, or number of elements in S, is less than or equal to the number of elements in the cross product of S with itself. Any ideas on this one?
I would say for every set, I don't know. That's what's getting me, is the for every set, that I think that would be false.
Yeah, so yeah, it's always kind of scary to say like in every case, but we can use some properties of counting methods that will be helpful to us. So let's just say that the size of S, has n elements. So then the number of elements that are in the cross product, we always know, so if there's a cross product A cross with B, then the number of elements in that set is going to be the number of elements in A times by the number of elements in B. So if there are n elements in S, then S cross with S will have n squared elements, always. So we can say that, yeah, it's true. It will always be less than.
Would this be
n squared?
Oh, sorry, I didn't mean to interrupt you. Would this be false if instead of S cross S, it was like S and S, like, or S intersect S, if that makes sense?
Yeah, that would definitely be yeah, since we don't, so I think you're saying S is less than or equal to the number of elements in S union with like R. Is that what you mean?
No, literally S intersect S, if that makes sense.
Oh, S intersect.
Oh, I guess you're right. But S intersect S would always be the same, so never mind. But I guess you're right. If it was S intersect R, or like a different set, then it would mostly be smaller. Or you couldn't say for every set, I guess is what I'm saying.
Yeah. Okay, so now this next problem is talking about power sets, which we also have a rule for counting them, which is what?
Is it like 2 to the, oh man, I remember learning this, but
Yeah,
I don't.
right? Or
It's 2 to the size of S.
Yeah.
Is the size of the power set of S. So yeah, nice job. So in this case, we have the power set of the power set, which means we have 2 to the 2 to the number of elements in S. Okay, and then is less than or equal to the power set of the cross product of S, which will be 2 to whatever is in S squared.
Nice.
Makes sense.
Yeah.
You kind of glitched out there. I don't know if it's me or.
This case.
Oh, okay. No, that's not just you.
Okay.
I'm having some serious technical difficulty.
Okay, I think you're good now.
Hopefully that will work. I tried to connect to my hotspot instead and it did not work. So we're back on the Wi-Fi. Hopefully it will stay reliable. Okay, where did I glitch out?
You were just saying that the other side is 2 to the s squared, or 2 to the sides of s squared.
Okay. So, let's see. I can't remember how I figured this out last time. So yeah, I think my assumption here is, so we can just take away the bottom 2 because we know that that's always going to be there. So we can just compare 2 to the, and let's do the same thing we did last time. Let's call it n is less than or equal to n squared. And I believe that that comes out to be false. It should be. Because yeah, we could do a proof for this as well, but you can confirm after a few cases, like if n is 1, then we have 2 is less than or equal to 1. If we have 2, then we have 4 is less than or equal to, oh wait, that one actually does turn out to be true. And then if we have 3,
the first one would be false though. Yeah, right?
Yeah. Is equal to less than or, yeah. So this first one, the n equals 1, is already that's all that we need to know, because that means that it is not true. If we only had one element in the set, then the power set of the power set would be greater than the power set of the cross product. Whew, okay. Next one, we're looking at x or not x. So what is this one?
Is that true?
True, yeah.
And what about x and not x?
That's false, right?
Mm-hmm. Okay, last one. If a divides b plus c, then a divides b or a divides c. Any first guesses? Okay, so let's go through just what it's saying. So it's saying, let's see, a divides b plus c implies that a divides b or a divides a. Okay. So this is saying that b plus c is equal to a times some k, then the same. Actually, you know what? I think it'll be easier to write it like this. If b plus c mod with a is 0, then b mod a is equal to 0, or c mod a is equal to 0. Okay, so we can actually find a counterexample for this, which there's quite a few actually. So let's say b plus c equals 6, and let's say that a equals 6, and we'll say b equals 3 and c equals 3. So in this case, we would have this first is 3 plus 3 equals 6, and 6 mod by 6 equals 0. So we've met the hypothesis, but we run into problems when we try to do b mod with a, because that comes out to, let's see, 3 mod by 6 has a remainder of 3, which is not 0. So this one is false. Okay, lots of work here, but do all of those make sense?
Yeah, they do.
Okay.
Yep.
Let's move on. All right, so this one is unexpected value. Your company plans to invest in a particular project, and we have some probabilities for each of the types of money that we can win, and we want to determine if it's worth it to proceed with the project. Okay, so we're also told to let X be the value of the amount of money you make, and either positive values or the amount of money that you lose, which would be negative values. So I think the easiest way to do this problem is to kind of split it up. So we have X, which equals however much money you get, and we have the probability of X. So what are the different amounts of money that we can get?
So, I mean, it says there that you can lose $2,000 is one of them, right?
Okay, so we can have minus 2,000, and the probability of that is 0.4. Okay, and the next one.
I'm assuming the next one will just be 0 because you're breaking even, right?
And that one has 0.4. And the last one is 5,000. And what's the probability of that?
0.2.
Okay, so to find expected value, we just need to multiply each of these like sections and add them together. So negative 2,000 times 0.4 is 800. And then we don't need to add in this because it'll just end up being 0. And then we have 5,000 times 0.2, which is 1,000. Or sorry, this should be negative 800. And then 1,000. So this comes out to $200 total. Okay, what does this $200 mean? Like, what is our interpretation of it?
That is basically what you should expect to make off the project.
Yeah, so on average, you expect to gain $200, which means that you can proceed with it. Okay, any questions on that? Okay. That one's more straightforward. Okay.
I like those ones.
All right, so this one is a combinatorics problem. So we are counting the number of ways a player could be dealt a spade flush. So that is 5 spades. Okay, so with the counting problems, there are always going to be like a lot of different ways to go about it. But I think, at least personally, I find it a lot more helpful to get to a formula and to use an algorithm. So I like to figure out, the 2 important questions, which is, do repeats matter? Or are repetitions allowed? And does order matter? So can we be dealt the same card twice?
No.
So repeats aren't allowed. And does the order of the cards matter?
No.
Exactly. So if repeats don't matter and the order doesn't matter, then that leads us to use a combination formula, which is C and R. Okay, now we need to figure out our N and our R. So the N is always the pool that you're choosing from, and the R is the number of ways, or the number of things that you want to get from that group. So our R is more obvious this time. How many do we want to pick?
So we want 5, right?
Mm-hmm. Okay, so the end is a little bit tricky here. Remember, so we're playing out of a deck with 52 cards, but we're only looking for the possibilities in which that card is ace, or all 5 cards are spades. So what do we want to pick from?
So is this, maybe this is like too in depth. Is this 52 choose 13 for N, or is that because there's 13 cards in the suite, right, that are spades, or the suit, and there's 52 cards total. I don't know. I'm not sure entirely how we get to that.
Okay, so let's think. We know that like a successful hand, or like what we're trying to count, is just a card with 5 spades, right? And we're not looking for probability, so we don't really actually have to worry about all 52 cards, because if one of these cards isn't a spade, then we just don't count it. So we would be more if we were finding a probability, but since we're just counting, like, think of this as an event, and so our sample space would be 52 pick 5. But the event itself is just getting 5 spades, so we just need to pick out of the 13 spades that are there.
Gotcha. So, okay.
C13, I'm going to make a note that that's the sample space. 13, choose 5, which is going to be, and you shouldn't have to multiply these out, but I think it can be helpful just to sanity check yourself sometimes. Oh, wait. So we have 13 over 5 factorial, 8 factorial, and we can do 12, 10. I always skip 11. I do not know why. Okay, 11 times 10 times 9 over 5 times 4 times 3 times 2. And then we can simplify some of these terms. And let's see. That comes out to 13 times 3 times 11 times 2 times 3 is 2574 over 2. And that is 1287. Okay, next we're going to do part B, which is solve problem A if the player is dealt an ace high spade flush. That is 5 spades. 5 spades with the ace. Okay, so in this case, our ideal, we're going to have these 5 cards, except one of them has to be an ace. So let's see. So first we want to pick the ace. Pick the ace. But there's only one ace that is also a spade, so there's only one way to do that. And then after we pick the ace, we need to pick the remaining cards. So this time, how many are we picking out of?
12, right?
Yeah. And we're picking how many?
4.
4?
Mm-hmm. So let's see. It'll be 12, 4 factorial, 8 factorial. That gives us 12, 11, 10, 9 over 4, 3, 2. And that gives us, let's see, 3 times 5 is 15. 15 times 3 is 45. 45 times 11 is 495. Okay. Any questions on that one, or any other?
Do we need to add 1 to 495 for the one way that we picked the ace, or is that a multiplication? I just can't remember.
Yeah, that's a good question. So because these two are like steps, that's kind of how I think of it, is first I want to pick the ace, then I want to do this. But because it's then, that also means and. So that means we want 1 and 2, and that means multiplication.
Okay, gotcha.
495 times 1. It'll be 495. Okay, any other, I know that difference between real and sum and product has been a confusion spot for a lot of people, so do we want to go over any more of those kinds of problems? Or does that make sense?
I usually can figure it out if I think about it, but I don't know about Lance.
I think I'm good.
Okay, awesome. The main thing just to remember is, are they in the same case or are they not? Like, is it something that you're having to do to create the one case, like how you have multiple steps in one case, or is it a totally disjoint situation?
Gotcha.
Problem 4. Probability question. What is the probability of getting at least 2 3s on 5 tosses of a fair 6-sided die? So what's the instinct here? What strategy do we want to use?
Trying to remember. We did a ton of these. I can't remember anymore.
I'm guessing you're looking for Bernoulli trials. Is that?
Yeah.
Okay. Yeah, so Bernoulli trials, that's where we have like C and R, like the P to the, let's see. Yeah, all of that whole formula, which I don't have memorized off the top of my head, but definitely a good one to put on your cheat sheet. Okay, so yeah, so we know we want to use Bernoulli trials. There's also another thing here, which is that we have at least 2 3s. So we could either solve it by doing 2, 3, 4, and 5, or I find it easier to do the complement in this case, because that'll just involve finding 0, 1, and 2 3s, which is like one less case, but something a little bit smaller. Okay. So in order to find the probability of getting 0 3s on 5 tosses, so let's start with our combination. What is this going to be?
So you would do, I'm trying to think, and now I can't. So sorry, I just went blank, so maybe Lance got something.
Okay, so when we're doing Bernoulli, I think there's a lot of confusion with Bernoulli trials about, like, I think everyone knows the formula, but I don't know if everyone knows why we use the formula, which I think is helpful to understand what's going on. So when we're doing Bernoulli trials, we're basically taking, let's see, in this case we have 5 spots. We want to fill those up with tosses of a fair coin, and we want to figure out the probability. So the first step is that we want to choose which out of these spaces has a success or failure. So out of 5 spaces, and we consider a success in this case is, or let's see, let's call it P. So P is the probability of success, and a success is getting a 3 on the die. And the probability of getting a success is 1/6. Okay, so in this case, we're saying that there are 0 3s. So out of the 5 spots, we're choosing 0 of them. So this one is actually not the best example. I'm going to hurry and skip ahead to one. So in this case, we're choosing one of these 5 spots to put a 3 in. And we can do this because all of the other spots just kind of default. So if we have a 3 here, then we know we have, like, not a 3 in all the other spots. I'll put 3 complement. That'll be better. Okay, so, but now that we've picked our spot that has the 3, we're not quite done, because that tells us how many ways there are to get the solution, but it doesn't tell us the probability. So if we were going to solve this without Bernoulli trials, the way we would do it is to figure out the probability of each of these spots and then use rule of product. So if the probability of not getting a 3 is 5/6, then we would have 5/6 times 5/6 times 1/6 times 5/6 times 5/6. And Bernoulli trials just kind of takes away a little bit of that work because this is equivalent to 5/6 to the 4th times 1/6 to the 1st. And that'll be the case in any of these. So now we add in that 5/6, or let's do a success first. So we have 1/6 to the 1st power and 5/6 to the 4th power. Okay, so basically, and that'll help you with the kind of problems we do where it's like a best of 5 and you know that this is filled up. That explains why. So like, sorry, if we were doing a best of 5 and we had 4 or 5 blanks, and we know that the last one has to be a 3, then now we do our combinations only from these 4 spots, but we still need to, if we filled in the rest of these spots, we still need to have the probability of this last spot, even though we know it's there. So that's why we would use 1/6 squared, 5/6 cubed, even though 2 plus 3 is not equal to 4, which we used in our combination. Okay, that was kind of like a long-winded rant, but does that all make sense?
Yeah.
Okay, so back to our problem. We picked 0 spots for the 3s, so now we multiply it by 1/6 to the 0 and 5/6 to the 5th. So what is this last case going to be?
Out of 5, you're going to choose 2, right? And then you're going to multiply by the successes, so it's 1/6 squared times by 5/4 to the 3rd.
Okay, so now we want to add all of these cases, but we're not quite done. What else do we need to do?
Oh, well, we found the complement, so you'd have to subtract it from the total number, right?
So, and in this case, this is also a common confusion with complement, is so since these are all going to get us probabilities, we can subtract it from 1. But if we were doing combinatorics, then we need to subtract from the sample space. Does that make sense?
Yeah, that does.
So yeah, this is kind of like not the prettiest way to present the final solution, but there we go. That's the probability of getting at least a 3. Any other questions on that? Okay. All right. I'm actually, if you're okay with it, I'm going to skip this problem since this one was just in our last discussion, I think. But if whoever teaches your discussion session, if they didn't have a chance to get to this one, I can go over it as well.
I'm okay skipping this one.
Okay. Lance, are you good with that?
Yeah, that's totally good.
All right. Problem 6, we want to determine whether each of the following is equal to A, the empty set, or the universal set. So let's just go through each of these. A intersect with the universal set.
That's going to equal A.
Mm-hmm. A minus A.
Null set, empty set, whatever you want to call it.
Okay. A minus the universal set.
Let's be a complement, right? Or no?
Not quite.
Is that still a universal set? I don't know.
Let's do a diagram for this one. I think it'll be good. So here's our universal set, and let's just say we just have A. I'm not going to worry about B. Okay, so this is everything in A, but then we're going to subtract everything that's in the universe. And A is in the universe, so it means taking away like just this entire box. And that means that pretty much everything gets wiped out. So this leaves us with the empty set again.
Okay.
Okay, A minus the empty set.
Just gonna be A.
Is that A?
A minus a complement.
Still gonna be A, right?
And last one, a complement complement.
Just
Is that
A.
just A?
Yeah, lots of A's. Okay, now suppose A and B are sets, and we have, we're going to use the power set definition and use a direct proof to show that if the power set of A is a subset of the power set of B, then A is a subset of B. Okay, so with we're told to use a direct proof, and it's not explicit, but we can kind of assume that means an element-wise proof, since that is the most direct way to do it with sets. So we want to, again, I think we did a problem like this earlier, where we have X is in A, and we want to use this definition to show that X is in B. And this is a little bit different than is usually how we do like a proof with a hypothesis. Usually we start with whatever is in the hypothesis statement and then we prove the conclusion. But with sets, it's a little bit different. So we want to start with the conclusion and then use whatever's in the hypothesis to support it. Okay, so if X is in A, then what can, let's see. We want to be able to say something about the power set of A. This is something that we know. So that kind of gives us a hint. Everything that's in the power set of A is a set. So we can say that if X is in A, then the set that just has X is a subset of A. And we also know that X, or the set that just has X in it, is in the power set of A. Okay, now what can we do? We know that we have an element that's in the power set of A. What else can we say about that set?
So I guess I'm just a little confused. Are we given that that means X, which is in the power set of A, is also a subset of the power set of B?
Mm-hmm.
Or is that what we're trying to prove? Okay, gotcha.
Okay, so yeah, that just has to do with that the kind of the backwards like set proofs are just kind of weird. So yeah, so we're given, we can assume that the power set of A is a subset of the power set of B. So what does that tell us about this little mini set?
That X is an element in the power set of B.
Yeah.
So X is in the power set of B by definition of subset. Okay, and that also means that X has to be in B because everything in the power, every element in the sets that are in the power set is going to be in the original set. So we can say that X is in B by the definition of power sets. And now we've shown that X is in A implies that X is in B. So A is a subset of B by definition of subset. Okay, does that follow?
Yeah.
Yeah.
Okay, awesome. Okay, it looks like we've just got a couple of minutes left. So let me glance through. I think it would be helpful to do one of these graph proofs because they're really tricky, but I'm worried that they might take up too much time. Yeah, let's do, I'll let you pick. Do you want to work on problem 11 or problem 12?
I don't care.
Yeah, one of them is an induction proof for graphs, and one of them is a proof by contradiction, if that makes any difference.
Let's do the induction proof, if that's okay.
Okay, yeah.
I agree with that one.
Okay, so, and problem, let's see. This induction proof also uses from the last problem that any plane graph with more than 2 vertices has a vertex of degree at most 5. So we're trying to prove, that any plane graph can be 6 colored. So the coloring is done with the vertices. So what that kind of tells me is that a proof by induction would involve something with the vertices. The vertices is going to be what's increasing because that's what we kind of don't know. So our problem statement, we can say P of n is that a graph with n vertices can be 6 colored. All right, and then our base case, we can just use, let's see, Pn is less than or equal to 6. And that's kind of like unusual for a base case, but the reason we do that is because the 6 colors, or 7 vertices is where we start to run into difficulties with this. So with each of, if any graph has like 1, 2, 3, 4, 5, or 6 vertices, then we already know that there isn't going to be a duplicate color. So it's impossible to duplicate any colors with less than or equal to 6 vertices. Okay, so now let's go into our induction hypothesis. And in this case, we're going to assume n minus 1 as long as n is greater than 6 is true. So this is kind of assuming everything from 7 up until n minus 1. And then our induction step is to prove P of n. So this is kind of like the bulk of the proof. So we can say, so that means that G is a graph with n vertices. All right. And n is greater than 6. We know that as well. And this is where we can use our hint, which is that any plane graph with more than 2 vertices has a vertex of degree at most 5. So we know that there exists some vertex U with degree less than or equal to 5. Okay, so remember we're trying to show somehow that each of these vertices can be colored without repeating a color. So let's go ahead and remove this vertex U because that will give us a G prime that we already know is true. So if we remove U to get G prime, which has n minus 1 vertices. So that means that G prime can be 6 colored. Sorry, we're going a little over time here. Okay, so that looks like a 6, and that should be G. G can be 6 colored. All right, so U has degree of less than or equal to 5, right? So let's add U back. And it is only going to, it connects to 5 neighboring vertices. And U connects to no more than 5 other vertices. Which means that out of those, we already know that those 5 colors are all going to be different if they're neighboring. So we can choose a color that is different from all its neighbors. So whatever those 5 colors are, those 5 vertices are colored. You can be colored the last remaining color. Okay, and that proves that G can be 6 colored. So this one is kind of confusing. It took me a few minutes reading through it and understanding it before I got a hold of it. So if it's not making sense, that's totally fine. I can answer any questions, but it also just takes some processing to understand what's going on here. And the important thing to take out of this practice problem is just that method of removing vertices and edges is really popular in graph proofs. So just being comfortable with that kind of process of, okay, I'll take away an edge and a vertex, edge or a vertex, and then I'll say something about that, and that G prime gives me important information about G.
Okay, that sounds good to me. I've actually got to go, so
Okay,
thank you for your help.
Thank you for coming. I appreciated the question.
Yeah, thank you so much.
All right, good luck with your final. You're both gonna do great. I have
Sweet.
faith.
Thanks.
Sweet. Thank you. Have a good one.
You too.
Bye.